Good afternoon. Welcome to concurrent session C3, Flood Risk Assessment in Complex Urban Environments. Before we get started, a few housekeeping items. One, you'll be able to provide questions in the question and answer session after the presentation. Please enter them in the little chat box there and submit it, and then we'll get them on there. You'll see chats that will come up there with the questions. If you see a question that's similar to one that you're interested in or if you think it's a really good question, or you see the thumbs up, let us know, select that, and that will rank it up there. The ones with the most thumbs up are the ones that I will ask. And also, please send your questions early. We'd like to get them in as soon as possible so that we have questions so that I don't have to make them up. Following this session, there will be, encourage everyone to visit the exhibit hall. There will be some activities tonight available that will be social events. I know that Tetra Tech is offering some type of competition of something, so you might want to check that out. Also visit the ASFPM and Flood Science Center booth. You can check it out, and if you look close enough, you'll find an opportunity to register for a $200 discount registration at the next year's conference in Orlando. My name is Bill Brown. I am with the ASFPM Flood Science Center. So with that, we'll get ready to introduce our first presentation. First presentation is choosing the right model to estimate urban flood risk in the continental U.S. Our presenters are Sangameswaranm and John Payne. So with that, let's go to the video.
Good afternoon, everybody. Today's talk will be on choosing the right model to estimate urban flood risk in the continental United States. We would like to thank ASFPM for the opportunity to present on this topic today. A brief introduction. My name is Sangameswaranm. I'm a project manager with Dewberry engineers in Fairfax with the Resilient Solutions Group. And John Payne manages the Hampton Roads office of GKY. A brief outline of our presentation. The purpose of this talk, the key definitions that we should be keeping in mind in the flood risk, flood hazard context, followed by a series of case studies by Dewberry and GKY using the different models, frameworks, and solution approaches. And then finally, some significant conclusions followed by Q&A. The purpose of this study is the images that we see on screen here. Natural disasters have completely changed the topographic, demographic, socioeconomic landscapes of the planet. Flooding events are on the rise, not only during the annual hurricane season, during the rest of the year, and we are recently seeing an increase in probability and the intensity of the events and the damages they cause. Few key definitions. Risk is always a function of hazard and vulnerability. Understanding the various components of hazard, the different variables influencing each component, the nuances of the natural and built environments is essential to quantify risk. The primary focus of this talk is going to be on the hazard side and the commonly available methods and our experiences with them. So hazard is a function of the various pathways, the intensity and duration floodwaters can reach a particular location in the continental United States. Common pathways are riverine, coastal, which includes storm surge, waves, wind-driven tides, and rainfall, which is cloudburst and pluvial, and also groundwater-based. So urban flooding, as we see, is typically a result of one or more of these factors that happen individually or in combination with others. So causes of any of these events would be meteorological, oceanographic, event-triggered or operations failures, including levee or dam breach, and accelerated climate change due to anthropogenic activity that in turn impacts many of the factors. So the available methods. Quantifying impacts needs detailed analysis of all the causal variables and the interplay of the different causal variables. Commonly available methodological options include empirical relationships with watershed numerical models and deterministic analysis approaches. Probabilistic and stochastic approaches investigate a range of events which have different intensities and durations. And the difference between probabilistic and stochastic being stochastic are more random events based. And machine learning methods are currently being explored, correlating flood risk with independent variables. The methods to the left are more watershed, physical processes based, and to the right are more data driven. So commonly available models and frameworks include the Army Corps' HEC suite of models for Riverine flood hazard analysis, conveyance models, which are groundwater models, and combined modeling frameworks. Our personal experience is there's no one model solves all kind of solution. The approach that has worked for us is coming up with a set of key questions that we are trying to answer for a client in a particular project. And then through a process of streamlined stakeholder coordination, we obtain both the data sets and then also seek inputs in terms of methodological recommendations from clients. So using those inputs and the available data sets, develop a methodology that would solve the problem, followed by the implementation, either on standalone computers or trying to run cloud instances of the various models to get at the scale that we need. So using this approach, come up with a hazard estimation, go back to the key questions and make sure that our questions and concerns are answered, followed by risk assessment, which would be a site-specific or a structure-specific loss estimate. John and I will present different case studies using the same model tailored to different situations and then different end results so that we can have a comprehensive picture of what these models can do and how it can be helpful for us. The first is of the HEC suite of models. ERDEC has made significant strides upgrading HMS and RAS leaps and bounds, especially with 2D functionality. The entire HEC suite, WAT, HMS, RAS, SSP, RedSwim, etc., providing the much needed open source solution of the future. With this, I would like to turn it over to John for a couple of HEC-RAS case studies by GKY.
Thanks, Siva. I want to start out with a somewhat unusual application of HEC-RAS. This is 2D modeling, but it's unusual because there was so much urban infrastructure here. This is Hurricane Matthew, and this was a model that we had done as part of a resilience plan for the city of Chesapeake, Virginia. And you can see with the detailed terrain in there and then supplemented with Google Earth imagery in 3 dimensions that you can get a very, very nice, whether or not it's accurate depends, but a very nice representation of flooding that pretty much anybody can understand. This is the layout of the watershed. It's just showing you on the left, it's really a system of linear canals and lakes. All of them are interconnected and flowing from the bottom of your screen to the top, from the south to the north. And on the right, you can see the digital elevation model. It's pretty flat, it's in Hampton Roads, Virginia, not a lot of topographic relief. So a lot of everything that's going on is being driven by the storage in those canals and those lakes. The city asked us to get involved because they've done multiple studies on this watershed for a long time, and they felt like anything under a 100-year event, they had pretty good recovery time. But when they really got socked, as they did with Matthew, that the intersections were long to recover. So emergency vehicles couldn't get through, and that was a real problem, as was just the pure flooding elevation. And you can see an aerial photograph that was taken at 7 a.m. on the morning after Hurricane Matthew blew through. And we were able to, on October 9th, if you look in the upper right of your slide, 2016, October 2016, that we were able to calibrate the model to come up with really surprising to me, matches between what was seen in the photograph and what HEC-RAS could do. And this is showing a profile that was generated within HEC-RAS, a very professional looking output. And what we're doing is looking for ways to improve the resilience of the watershed. So we're looking at culvert crossings where there's significant head losses in here. Significant depends on your sense of humor and your willingness to spend a lot of money. But we would consider those crossings for culvert upgrades. But the interesting part was next click, please. When they constructed the interstate back in the 60s, they, for some reason, left the culverts way elevated, and that created upstream storage. So even though the upstream culverts are much lower, it created that system of lakes and keeps it permanently flooded. And the solution for this problem was to lower the culverts under I-64, or to provide an additional culvert, low flow culvert, and create a tremendous amount, a significant amount of upstream storage in those lakes. And this is showing one location that was particularly bad. We're able to go in HEC-RAS, it's a dynamic, hydrodynamic 2D model, and pick out an elevation 15.32 at which that intersection is impassable. And we plot that on a graph that we call a resiliency plot, and take a look at existing versus improved conditions after we put in the new parallel culvert under the interstate. And you can see that we dropped the recovery time. In fact, there is no recovery time because the intersection stays open, but it reduces the recovery time by 34 hours from Hurricane Matthew. And also that there's a decrease in flood storage, decrease in flood stage of 1.62 feet. So nowhere near as many structures are flooding. This is a application. I've grown up in Hampton Roads, and the Corps of Engineers did a HEC-RAS 1D model and a flood insurance study in 2016, an update. And they contradicted what I knew in my heart to be true of the watershed, because I'd done all kinds of modeling around here. This is a digital elevation model showing the Newmarket area, and you can see a large drainage canal going to the southwest. That's out to the James River. And it's a 9,700 acre watershed, but a lot of upstream flow comes from the top of your screen and then out to the southwest through that canal. And you can see from the terrain, an entry-level intern could delineate this properly and see that the major divide is the dashed line there, and that flows are to the north and south from there. And if you go one more, where we drew that line in the 1970s, they built a weir, shown in this photograph, to ensure that those flows were not interconnected. So in the north of the picture, everything goes north, and in the south, it goes to the south. So that's the watershed divide line there. You couldn't ask for a clearer version. But when the Corps did the new flood insurance study, you can see they ran the floodway right through three shopping centers, actually. I'll see if you can click. And you can see there's the floodway. And instead of making the turn and going out to the southwest, like I was absolutely certain it would, the floodway was drawn with a 1D HEC-RAS model going straight to the south. And here you can see from the flood insurance study profile that they drew the flow going downstream when in fact, where it should have gone out to that southwest confluence, they were actually bucking grade the whole way. And they were saying that the flow was going to continue in the upstream direction and spill over Mercury Boulevard and flood-free shopping centers. And I just knew that wasn't right. So we created a HEC-RAS 2D model for this. And you can see this is a design storm, so a NOAA Type C 24-hour hydrograph. So at 12 hours, you get the peak flow, but you can see at 12 hours and 30 minutes, so 30 minutes after the peak rainfall, the flow is exactly in the direction that I expected in that ditch. It's going out, the flows are seriously going towards the James River. However, at 12:45, it's a different picture. The flow reverses, and now it's going to the southeast, and it is going to flood those shopping centers. And we can see this in a model. This is the 24-hour storm. You can see the flood starting a very, very urbanized watershed. And when you get to 12 hours and then 12 and a half, you can see the flows starting to drain out. It's actually reducing the flow. However, as it continues to go to 12:45, you'll see an overwash from the upstream load. The upstream watershed arrives and does exactly what the Corps of Engineers said it would do. It, if you'll proceed, Siva, it floods in the downstream direction and floods out three shopping centers and moves down there. So bottom line is the Corps was right, I was wrong. But the only way you can really prove this in a 1D model, of course, you have to assume the direction. And in this case, with the 2D model, you can actually prove that the flows go that way. So the whole game is being played on the terrain. And we can confirm exactly when that washover happens by drawing a transect in HEC-RAS and plotting the hydrograph at that point. And we can see that the flow is in the negative direction, which means in this case that it was flowing to the north, and then it reverses at 12 hours and 35 minutes and flows to the south. So we're able to get very, very precise with the HEC-RAS 2D modeling.
Thank you, John. So moving on to some large-scale studies that we have been able to successfully implement using RAS-2D. The first one is the City of Houston unmet needs right after Hurricane Harvey. Dewberry generated an unmet needs estimate using 2D hydraulic model that spanned 1,500 square miles of Houston city and the vicinity. Precipitation data was downscaled and reconstructed and applied as meteorological forcing on the 2D mesh. So using this approach, the impact of Harvey in the areas of impact were actually predicted with a high level of confidence and matched very well with both the high water marks and the reports based on the impact data. Our study helped direct the funds to recovery programs and served as the basis for planning and outreach for housing activities using CDBG DR funds. Moving on to a series of urban stormwater models, swim engine-based models for hazard assessment and mitigation planning.
This is a combined 2D, 1D swim model. It's actually PC swim, and it's in Fairfax County, where there was a huge pluvial event that flooded many neighborhoods and many structures. But these are 4 of the structures that got blasted. And you can see we've created the 1D storm pipe network in there. And this is actually a bowl. So if you look at the topography, you can see, I'll show you, it shows up more clearly in the next slide, that the area of interest where the homes flooded is in that saddle area. And what we're interested in doing is providing 1D improvements, what can be done in terms of adding pipes and doing bypasses and things like that, adding inlets to reduce that hydraulic grade line to keep those homes from getting flooded. And the interesting part here is if you look at the 2D, you can see the flows in the pipes are going to the north and out through the drainage outfall. But as this event occurs, this is a 24-hour design event. It's very, very flashy, so you have to catch it very quickly. Flood waters don't lay around very long. But those 3 homes in the middle there get just absolutely wiped out with flood water. So this has been a really helpful tool. We modeled it first with HEC-RAS and did not have all the intricate, detailed storm sewer network in there. And then the county asked us to go out and do the surveying and pick up the drainage infrastructure. And at that level of detail, we really needed the power of SWIM and its engine to compute the pipe flow hydraulics and then combine it with what was happening on the terrain to come up with some solutions.
So moving on to a interesting example using PC Swim Professional 2D for a resiliency study for Clover Hill neighborhood in Frederick County. This was an interesting project, first of its kind, where we tried a rain-on-grid approach, and we validated the model using resident survey questionnaires, both anecdotal and high water mark type data wherever available. And we tried a series of events, the 2-year, the 10-year, and the 100-year, and we were able to predict pluvial flooding very, very accurately. And the results of the analysis are useful for sustainable flood risk reduction measures, and are also currently we are developing water quality, TMDL, NIBD's compliance oriented stormwater BMPs, and this will definitely serve as a template for other areas within the county. Another interesting example is using XP swim models. This is the Naval Academy facility in Annapolis, Maryland. So the red, yellow, green dots are the key areas of reported flooding within the facility due to increase in sea level rise and also localized ponding due to rainfall events. This study was interesting because we used XP swim model 2D network to simulate the increase in sea level rise coupled with precipitation impacts in the overland areas. So that's existing conditions, and that's the future 2100 based tidal conditions. About 44% of the facility is under the risk of being inundated, and flood risk management strategies that we developed included improved conveyance, drainage network redesign, and detention storage wherever possible, and pumping whenever inevitable. So the drainage retrofits for the current conditions, for the future conditions, you see that red flood wall line along the perimeter, which is going to be required for the future conditions. The network redesign, that's the current conditions plus flood wall and pump station to handle the end of the century scenario, subsurface storage wherever possible for the current scenario, that plus the flood wall for the 2100 scenario. So very interesting applications, 2D rainfall on grid coupled with tidal boundary conditions with and without sea level rise, which was very useful for coming up with courses of action, pointing to a recommended course of action for flood risk management consideration by the DoD facility. I'm going to talk about coupled model solutions, so useful for hazard assessment and mitigation planning. How would you model a system like the city of Virginia Beach, where water can enter from the Atlantic Ocean side, Chesapeake Bay side, the open water, wind-driven tides from the Back Bay side, and watershed contributions, which would result in anything between sunny day flooding and extreme flooding, cutting access, and then infrastructure impacts. So the solution that we came up with and was successfully implemented was the hydrology was done in PC swim because of the methodological requirements by the city of Virginia Beach, and Mike Urban for coupling the urban stormwater pieces, and Mike 21 for the wind-driven tide impacts with and without sea level rise. So we were able to develop a coupled comprehensive watershed model because of the physical coupling between these pieces that talk to each other, resulting in a comprehensive flood risk picture. This is no rain plus wind tide and no sea level rise, 100-year rain plus wind tide plus no sea level rise, and that scenario with 1.5 feet and 3 feet sea level rise. Some of the statistical solutions would involve expressing flood vulnerability as a function of watershed conditioning factors. An interesting example is the application in the Currituck County, the rainfall vulnerability study. We trained the model using point data available for flooded, not flooded, and developed a logistic regression analysis, which resulted in flood susceptibility as a percentage. And because of that, we were surprised to see that a lot of critical infrastructure that's not within the identified FEMA flood zones actually were vulnerable as predicted by the logistic regression model. Another interesting experiment that's ongoing is the use of machine learning models. Training data based on watershed models will already have a great correlation between the dependent variable and the independent causal parameters. The problem that is the test data is being limited and sporadic. Some of our ongoing experiments include artificial neural networks and random forest methods, which are basically two of the most promising methods that we have found. As have other researchers, including Google AI, the graphic on the right bottom. The key findings of my team have been that training data based on watershed models can result in better informed machine learning models. And that's where the entire open source movement can help make these models as intelligent as they should be. So in closing, is there a right model to estimate urban flood risk in the continental United States? No, there is no one single model or framework. The solution calls for a systematic understanding of the needs, goals, constraints, and priorities, and collecting and consolidating and analyzing all the available data sets and models, and standardizing what's usable to get the answers that we started with, and using engineering, science, and technology to develop large-scale, optimizable, scalable, and reproducible solutions that can give us statistically significant flood hazard estimates, and therefore flood risk products would be the best model to estimate the urban flood risk in the continental United States. Thank you for the opportunity, and we would be happy to take any questions. Our email addresses are on the slide, and you're welcome to stop by at our virtual booths, where we'd be eager to share insights and details on the case studies that we presented and more studies that we did not have a chance to present because we had 25 minutes. Thank you so much.
Welcome back for the question and answers portion following our first presentation. I'm here with Siva and John, and I'll be asking the questions. Encourage anybody out there to submit some questions. We're a little lacking right now, but we'll get to the one question on the board. Siva and John, you provide examples of steady state models for your presentation, but absent was basically, the steady state scenario compared to mostly dynamic. Do you see a future for steady state models in modeling complex urban systems?
Yeah, I guess I'll start with that one. One has stream restoration Clomer project in there in the slide deck, but we had to cut it for time because it was the least interesting, to be honest with you. I think, yes, there's no way of getting around 1D. It's legacy, it's here for a long time, but I will say, in the choice, I've been doing this a long time. I would strongly prefer to do a 2D over a 1D, just because I don't like the assumptions that I have to make when the hydraulic line breaks the ground elevation. And 2D does a much better job with that. It's less expensive than if you're starting from scratch and tilt up a 1D model. My ultimate preference would be to do a combined 2D, 1D, but a lot of times a client's not willing to pay for that or doesn't have the time or whatever. Yeah, I don't think 1D is going away anytime soon.
Any comments on that, Siva? I'm not getting any sound from you.
Can you hear me?
Yeah, now we got you.
Yeah,
thanks.
Sorry. To add to what John said, steady flow is still very important when we are looking at conservative situations for stream restoration or stream bed armoring kind of design. Say, for example, the St. John's River in the city of Jacksonville. There is a narrow section where there's riprap or there's like sheet pile wall line channel that connects portions of the urbanized parts of the city. So there we would look at a combined occurrence of 100 and 500 year surge events with a static condition and the flow rate from the upstream that would also be put in as a static condition, which is essentially steady flow approximation or a quasi steady flow modeling of a 2D model.
Okay, got questions coming in now. So how did you come up with design conditions combining riverine and coastal, joint probability or something else?
Yeah, joint probability and also a statistical analysis of the combined occurrence of both these events. The publication is on the City of Virginia Beach's Sea Level Wise website. That's a study that we did, which informed the different scenarios that we were modeling. Because typically, an extreme rainfall event is not concurrent with an extreme surge event. It could be, but typically severe interior event is combined with a less severe storm surge type event.
Okay, great. What was the rationale for different model choices for each site? There's an overlap in the physics represented by the models presented here.
Okay, it depends on, like I originally mentioned in the talk, it's a combination of the fastest solution, the most efficient solution, and also addressing all the concerns of the stakeholders. I would like to take the City of Virginia Beach as an example again. They were very specific about the methodology that they wanted to use. For example, the modified green enamed as a method for the infiltration. So DHI Mike's mouse model in the version that we used does not support modified green enamed. So we had to use the PC swim as the hydrologic model and input the hydrographs into the respective nodes in Mike Urban coupled with Mike 21. So it's a combination of what's needed, what's the best methodology, and the most efficient way to come close to the right answer.
Okay. If you completed a study with machine learning, what sort of documentation would be submitted with the deliverable?
That's a great question. So some of these pieces of code are open source, and like a technical white paper, which lists out the assumptions, methodology, the data sets, like I mentioned in the talk. The test data set is what's very sparse and it's very valuable. So we would be relying heavily on open source data, if at all that's available. WASE currently has a connected citizen community program, and which increasingly municipalities are trying to, you can mark a point and report flooding, but even that only has a certain level of accuracy. So like a white paper with the different pieces that went into the analysis, and pieces of code that can be made publicly available through GitHub, for example.
Okay. Were any of these models used for Lomax? And if so, what challenges did you face?
Steve, do you want that one? My short answer would be I've done a fair amount of 2D modeling, particularly with the HEC-RAS model and also PC Swim combined 1D and 2D. But for Lomax, we've stuck strictly with 1D just because it's easier to push it through.
Anything, Steve, on your part?
No, that was pretty good. Thank you.
Okay. How has your experience been with setting floodways with 2D models? How would you set a floodway in a combined 1D and 2D model?
Floodway modeling using 2D models is still emerging, and there is no definitive right answer yet. I mean, rightfully, FEMA regulates the use of some of these models, and that's still emerging. So for floodway, still 1D is probably a more reliable approach. John?
Yeah, I agree. And my experience with FEMA goes back quite a ways. And we've had where we would submit fairly sophisticated models and then be told that they didn't have the capacity to do that level of sophistication. They preferred the simpler models. And that was, golly, I bet that's 25 years ago, talking about hydrodynamic 1D swim models versus steady state modeling. But I kind of learned my lesson, keep it simple.
Okay. Have you simulated any wave-related wall or dune overtopping or overwash mechanisms coupled with urban 2D domain? If not, how might you approach that?
Yeah, I can take that. So this was, there was a study for Lafourche Parish, that is FEMA Region 6. So there is a Larose to Golden Meadow ring levee system and 41 forced drainage areas, which are basically bathtubs protecting communities. For the Larose to Golden Meadow ring levee system, we developed a RAS 2D model. And the sources of flooding that we used were the wave overtopping. That's actually the waves above the levee crest and rainfall on grid, and the riverine contributions. So the mapping we came up with was a composite of all these three as required by FEMA's non-accredited levee analysis process.
Okay, ran out of time now, but I had a lot more questions, but I really appreciate your presentation here. Look forward to hopefully people, if you have questions, you can reach out to Siva or John and pose those questions to them. But with that, we're going to move to our second presentation, comparison of 2D HEC-RAS models, shallow urban floodplain with and without buildings. The presenters are Karen Kabbes, John Hood from Kabbes Engineering, and then Joe Kranzler with the Metropolitan Water Reclamation District of Greater Chicago. So with that, let's go to the video.
Hi, I'm Karen Kabbes. I'm with KEI. It's located in Barrington, Illinois and Fayetteville, North Carolina. And I'll be presenting today on 2D modeling of shallow urban floodplains with and without buildings. Presenting along with me today will be Joe Kratzer Joe's managing civil engineer for the Metropolitan Water Reclamation District in Greater Chicago, located in Chicago, Illinois. And also John Hood of KEI will be assisting and answering some of the questions you'll have today. What we're going to talk about, Joe's going to start with describing MWRD, their mission, and the Natalie Creek Flood Control Project. We'll be talking then about the shallow overland flooding in urban residential setting, how we decided to go ahead and look at updating FEMA floodplain map in a steady flow world, then using the 2D model along with the 1D unsteady flow flood control project model, then using LiDAR DEM to better define streets and buildings in that overflow area, creating a 2D model with that information, and then using that 2D model to compare looking at with buildings, without buildings, and changing N values, and looking at how that may change the results in the model. And then some of our general observations with 2D modeling effort. I'm going to ask Joe Kratzer to go ahead and take over and discuss a little bit more about MWRD and the Natalie Creek Flood Control Project. Joe?
Hi, I'm Joe Kratzer with the Metropolitan Water Reclamation District. I'm here to give you a little background about our agency and how we became involved in the Natalie Creek Flood Control Project. The MWRD was established in 1889 to protect Chicago's drinking water source, Lake Michigan. Our service area includes nearly 900 square miles and 130 communities, including the city of Chicago. In 2004, the Authority for General Supervision of Stormwater Management was granted to MWRD, and while our agency's mission has evolved, we strive to provide the highest standards of excellence in fulfilling our mission to protect the health and safety of the public in our service area. Since 2004, we have performed many studies and implemented dozens of stormwater projects to alleviate flooding across Cook County. One of those projects that you'll hear about today is a flood control project in the Natalie Creek watershed located in the south suburban communities of Midlothian and Oak Forest. While the result of a detailed watershed study performed on Natalie Creek clearly showed a significant problem, a group of residents that had organized around their collective flooding issue was just as convincing in demonstrating the need for a solution. The resulting project will provide significant flood relief through both conveyance improvements and additional floodplain storage. Due to funding constraints, the project will not remove all structures at risk from the regulatory floodplain. However, due to the extent of the watershed-wide improvements, a floodplain map revision is required to satisfy permitting requirements upon project completion. MWRD hired a team of consultants, including Burns & McDonnell and KEI, to provide engineering services for this project, including the LOMAR to be submitted to FEMA. This team has been involved in the project since its preliminary engineering phase all the way through construction. Karen Kabbes, who is leading the LOMAR efforts, along with her colleague John Hood from KEI, will take you through the rest of our presentation. Take it away, Karen.
Thank you, Joe. So let's talk about shallow overland flooding in urban residential setting. So Midlothian is the downstream community in the watershed of Natalie Creek. It's a very flat area with a number of homes and relatively small lots. Natalie Creek is a historic stream. It's been there on the earliest USGS maps with approximately a 3 square mile watershed. And just the reason why that's somewhat important is that many of the stream systems or small streams in the Chicagoland area are streams that have been created as part of the urban drainage system. The Natalie Creek was actually there in the earliest USGS maps. And for example, if you look on the left on the slide, there's a depiction of the 1901 USGS map that basically shows Natalie Creek. And I'll just go ahead and grab the laser pointer here. And here's that Natalie Creek watershed. And Natalie Creek, the stream itself. What's interesting to note, though, is you notice there's a big wetland area here in the center, suggesting with a nice meandering stream going through it. Now, located below that picture of the early USGS map is a current aerial photography, and actually it shows where the stream is located now, which is very much the same, though that wetland area right here no longer exists and has been drained and is now covered with a bunch of houses. What's fun to notice in this comparison of the early 1901 USGS map and the current aerial is they're actually about the same size and lined up pretty well. So here is the same street here as down here. This is actually what's called Pulaski or Crawford Avenue for those who are in Chicago. And here is Cicero. Again, here's a street here right below it. And this is 147th Street, which is also depicted here. Again, the creek system is more or less in the same location. And you see this old roadway that's on the current map that was also there in the historic map. And the railroad system, this is still there. So we'll be seeing these, the railway system, 147th Street and Pulaski Avenue are going to be shown in most of the photos or depictions we're going to be looking at. So by the late 1930s, this wetland area had been drained. And again, the stream had been straightened and the former marshy area was laid out for the street system. Then also by the 1960s, Natalie Creek that used to enter into Midlothian Creek, which is a creek that went along the railway system here, had been diverted to go up Pulaski, and that's what's shown here. It now drains about 8,000 feet to a man-made channel, about 8,000 feet to the north. And then by the 1970s, most of this land in this former marshy area had all been developed into these homes that you see now and street system. So here's the creek system, but what's been interesting to note is that there's always been this area of flooding that's come through this area. And you can kind of see that in this old map too, that there was sort of an overland drainage path through there, this area. So this area still experiences flooding over land when there's a significant flow. So here is the current floodplain map. Here's Midlothian Creek that we talked about. And there's Natalie Creek where the channel is, that straight channel piece. And this is the overland flow area. The FEMA map is based on certainly an older steady flow model. And the new flood control project that was being built is an unsteady flow model. We had looked at using that unsteady flow model to update the FEMA map, but IDNR, the state agency that also reviews floodplain mapping and modeling for FEMA maps, was not eager to have unsteady flow models used for floodplain mapping and floodway mapping, and asked that we convert that to a steady flow model. But looking at this overland flow area, the State Water Survey, which is the coordinating technical partner that reviews the floodplain map revisions for FEMA, said, you know, since it's a overland flow area, it might be useful with shallow flooding to look at it with a 2D model, since it's not really clear how this exactly flows through here. And because there was no floodway mapping, the state IDNR did concur in going ahead and using 2D modeling just to map this portion of the floodplain and have a steady flow model for this piece. So to get started, we clipped out this area with a nice LiDAR DEM, and having that good quality DEM was critical. Again, very flat area. We needed to be able to see the street system and that 8-inch curb and those yards that are right behind it and the houses, a very flat area. So we thought it would be very interesting though to look at here a DEM with buildings. So we went ahead and also took the DEM data and created a DEM that showed all the building systems. Since the floodwaters need to go through this really pretty dense neighborhood, we went ahead and captured that information of the DEM and looked at, would it be better to go ahead and instead of just using a higher N value to model that neighborhood in the overland flow area, would it be better to go ahead and actually use the data with the homes there and how they could potentially block the flow. So we imported that DEM data into HEC-RAS and here's the no buildings DEM in HEC-RAS and the with buildings DEM. Again, you can see very clearly how those houses line the street and again, how in some areas there are just a lot of buildings and garages and some very dense construction in those areas. So here is the recent land use map we obtained, and we tied different Manning's N values to different land use defined on the map. This red being mostly the residential area, the green, of course, being the street grid system, and then the commercial areas. So we basically used 0.15 for the residential areas when we had no buildings in the model. And then we did look at using 0.10 for the residential areas when we did have buildings. We used a 10 by 10 grid system for the cells that we used. And I think many of you, of course, are aware that the 2D model actually has water moved from cell to cell in different directions. And so we used a 10 by 10 foot grid for those cells. We used a constant flow input. Actually, we did two different ways. We had a constant flow input from the stream system over here coming out using the peak flows for the 100-year and 500-year. And we also did a hydrograph system where we basically used a hydrograph coming out from the stream. So we looked at it two different ways to input water into the 2D model system. Now, again, you see this pretty extensive neighborhood grid system, but we did not model any storm sewers as part of this. So that is one thing we did not do. Again, just to reference back to the system, you've got the railroad system here in the southeast corner of the map, and then towards the north across the map is 147th Street that we looked at before on even the historic map. And here's Pulaski Avenue on the eastern edge of that map. So let's look at when we put that hydrograph in, what happened as the water went through the neighborhood. It was really a fascinating experience to do this and to go ahead and actually show this to different folks who've been involved in flooding in the area. And it was really rewarding because to a large extent, what they saw here with the water coming down 149th Street, then moving up to 148th, then overland just south of 147th and flooding some of the neighborhoods, backyards there. It is exactly what they experienced during an actual flood overland flow event. So it was really, really very rewarding to have captured in this model what they actually see happening. And then what's also fun to do is to look at the particle tracing, which basically shows where the density of the flow or the particles are moving. And again, coming down 149th, that street sort of in the middle of the east-west street, in the middle of the picture, then flowing up to 148th Street, and then winding its way up again to 147th, flowing in that big neighborhood area in the back, the neighborhood back just south of 147th here. Very, very interesting, and again, replicates what people saw, what people actually experience when the flooding occurs in that area. So let's go ahead and look at the results we've got. Mentioned that we've got this area, pull up our laser pointer here, 147th Street again, 149th here, 148th. Again, the land is so flat in Chicago, it's very easy to do a grid system. And most of the communities, including Midlothian, that are near Chicago, even though Midlothian's about 20 miles southwest, it actually uses some of the same street names as Chicago. And so this is the area where the north-south streets are known as the K streets. So starting with 149th and Kilbourne down here and moving up to 147th and Karloff up here. We looked at the different elevations and considering buildings and no buildings. And what we found was that there really wasn't a lot of difference. Now, the flow depths weren't that great. You know, they were going from roughly a quarter foot to roughly just over a foot, foot and a half, except for that one big depressional area back in here, where it was over 2.5 feet. But generally, the differences were within a tenth or less, except for in that one depressional area that had about a quarter foot difference between the building and no building. So not a lot of difference for the 100-year flood. So we said, well, what happens if we actually look at the 500-year event? So we did go ahead and look at the 500-year event. Again, a little more difference here, The depths are about a half foot or more than the 100-year. But again, we're looking at primarily under 2/10 of a foot, and then about lower 3/10 in that one depressional area where the water is up to 3 foot deep, or just over 3 foot deep for the Floodplain event. So there really wasn't a lot of differences we were seeing by looking at the no building scenario. So we said, okay, what about the M value, the effect that Manning's M values have on the elevations here? And we did look at what happens if we, for the building scenario, look at, since we're already including buildings, look at a lower N value. And boy, we just did not see much of differences. So you're looking here at basic, we're talking hundreds between the no buildings model, the buildings model, and the buildings with lower N values, using a 0.10 Manning's index compared to 0.15. We just are not seeing a lot of differences. We're in the process of still going ahead and finishing up the FEMA floodplain model and mapping, at least for existing and for proposed conditions. Here is on the left the FEMA model that we had seen already, and our 2D model for the overflow area shown on the right. Now, certainly part of what we're seeing here is just a better resolution with a better DEM model that shows the street system and shows how the water moves through the street system. But it's interesting too to see how the water moves overland through those neighborhoods, and some of the neighborhoods that were not expected to be impacted are impacted, and some of the areas that have been impacted are not impacted as greatly as they were expected previously. So it really does a nice job of looking at really where does the water really go. So let's look about some of our general observations conclusions. So we found that in relatively shallow areas with low velocities, the 2D model was really not very sensitive to the inclusion of buildings from the DEM. So even though we had a pretty dense urban area, we just didn't see those buildings doing a lot to block flows. Now, we also looked at, how they could move water through the area, though. That was probably the most rewarding thing about this model, is being able to have the water depicted, particularly in using a hydroflow coming out of the main channel, flowing through that neighborhood, starting down the streets, then turning up and down some other streets, and then finally going to backyards, and really matching what people observed there. It gives them a considerable amount of comfort and relief, and really validates our model when they feel we've done a good job, when that model actually reflects what they really see happen during a major high water event. The other thing was really interesting about doing this modeling, of course, was that the 2D modeling really helped a lot, where you couldn't just simply put cross sections perpendicular to flow. We had an idea where we thought the flow line more or less was, but as you saw, to some extent, particularly that particle tracing model, it really seems to follow those streets until it starts working into a much bigger backwater or backyard water area. So it really helped a lot to figure out where that flow path was, and something that, very bluntly, trying to have put cross sections through that area would have required a pretty experienced modeler, and even that, the modeler would have been sort of guesstimating what actually happened. So what's nice too with having the 2D model, we can actually make some, if we just do decide we need at some point to have a 1D model or have cross sections instead, we've got a pretty informed decision in deciding where to put those cross sections in the future. And then just the last point, that the model processing time is, of course, very sensitive to the size of the grid. So just like to go ahead and end this, get ready to answer any questions. I'm just going to show you that particle tracing model again to tell you one of the men that GS guys that helped put this model together. He was showing his roommates, he's been working from home, and they were like, Wow, that's really cool. And these are people that are not involved in floodplain mapping or modeling at all. So there's something just very mesmerizing about watching that particle tracing model, with the movement of water through that area. But again, thank you so much. Happy to answer any questions you might have. Thank you for listening.
Welcome back for the question and answer session. We're here with Karen Kabbes, John Hood, and Joe Kratzler. So with that, we're going to get to our first question. Was the existing storm sewer system excluded because it was assumed to have negligible capacity to reduce surface flooding or subsurface flow?
John, want me to start that one?
Yes, go ahead.
That's a really interesting question. And we are trying to be somewhat simplistic in how we modeled this, look at the overland flooding, and also being somewhat reasonable, kind of trying to convey or contain how much work we did do. So at this point in time, it looks like the storm sewer system is not going to be considered significant, so it was excluded. But at some point in the future, that question may come up again. John, anything else you want to add?
Basically covers it, yeah, just
Okay. Next question then is, you mentioned that the state of Illinois was reluctant to allow you to use a 1D or a 2D model. What was their rationale?
From what they've told us, they're very concerned about having a model that's easy for the consulting community to use if they want to go in for a map revision. And their concern is if they have an unsteady flow model or a 2D model, it's going to be hard for the average consultant to pick it up and to make any kind of changes to that model. Right now, they have a state law that requires any kind of floodway work. For example, if you do any floodway work, you have to revise the model. If it's in fact, it results in differences in flood elevations or floodway widths. So I think their concern is that the consulting community won't be able to rise to the occasion.
And you used for this study, what model was it, HEC-RAS?
Yeah, on 2D HEC-RAS, correct.
But that's not readily that's not readily recognized by the consulting community in the Chicagoland area.
Well, I think it's more the issue of how easy it is for folks to use. And that's been a concern, is that at this point, again, the state's been not, the state's concerned about floodways. And that was in the earlier sessions, we talked about the issue of floodways in 2D models and how you do floodways. And that's still somewhat up in the air. It's though I think becoming more clarified now with some of additional FEMA guidance. But yeah, so that's been a big concern of how do we go ahead and deal with floodway issues with the unsteady flow models and the 2D models. So this was a unique case. And again, because there was no floodway defined in this overland flow area, that the state said, yes, you can go ahead and use that 2D model to look at that. And that was, again, the CTP, the coordinating technical partner, said this might be a really good application because the flow is going all over the place.
Okay. Why didn't you look at rain on grid at the same time as the Riverine flooding?
I'm gonna let John answer that one.
well, we basically just want the, we had the hydrology for the main stem, so we basically just looked at we looked at the hydrograph. We also looked at the steady flow input, and it's a fairly small area. So.
Okay, I got two questions, but they can pretty much be put together. They're on the in relation to the DEMs, the digital elevation models. What was the resolution of the DEM, and how did you prepare the DEM to include buildings?
Yeah, I can handle that. The DEM we looked at two. We had a 4-foot grid DEM, and then we also looked at a 2.5 foot. For the 2D model, we used a 4-foot DEM. And then what we had to physically go in, I don't think we had the categories of structures in there. So we actually took the raw data and then outlined the building areas, and then used those areas for the building for the DEM, and included those in the DEM with the buildings. And then without the buildings, we excluded those points.
Well, what was the vertical accuracy of the DEM?
That one, we'll have to get back on that one. That was
Okay. Looking through all the questions here. What is the dimensional cell grid, the dimension of the cell grids? Did you try different resolutions of the grids, and this will, and did this impact the create a difference in the water surface elevations?
the cell grid that we used in the 2D model was a 10 by 10 grid. We did try different grids because the 10 is really small, makes for a long running model. But we did not look at the real detailed comparison with other grids. We tried slightly larger, slightly smaller grids.
Okay. How did you treat areas that were not in the special flood hazard area on the FEMA map, but are in the 2D overflow area? Is there a hazard communication strategy with people who live in these areas that don't currently pay flood insurance?
Ooh. I don't want to flip that to Joe, but that's an interesting question. I don't know if at this point, there's certainly been the Flood Lothians folks that have been looking at all sorts of different flooding issues. And I think your question goes back to essentially flooding issues outside of what's mapped as the floodplain, because we certainly showed areas outside the map floodplain, right? Right, Bill? That's the question?
Yeah. Basically, for the areas that weren't shown as being in the subject of an identified special flood hazard area, but you show it in the 2D analysis, you've now identified risk. How is that being communicated to those who are potentially impacted by that risk?
I'll jump in a little bit and maybe not answer the question so directly, but not too indirectly either. The modeling that we're doing is going to show that not everybody from this project is going to be removed from the floodplain. I mean, that was communicated very clearly up front to the residents, the trustees, and other stakeholders, because when we studied this project years ago, we came up with a solution that could get 100-year level of service, but the cost of it was about $60 million, and the benefits were about $5 to $10 million. So it wasn't considered cost effective or justifiable from that standpoint. So we worked with Burns & McDonnell and KEI to come up with a solution that actually would be something that would provide significant increased level of service. It does take a few people or a dozen or whatever it is out of the floodplain, but it's really there to protect people from those more frequent events, knowing that there's going to be a bigger event that could still come out of bank. Now, I will say this, and I don't know if Karen has even heard this yet, but we're working with the Army Corps and USGS and some other agencies to see if we can put together a flood warning plan for this project as a result of a lot of the projects we will provide that higher level of service. This one, it was more challenging just because it's really so flat. And where we have projects like that, we look to kind of provide additional resources to the community, and a flood warning plan seems like something that they could benefit from. So we're working with the community and other agencies to try to implement that.
Okay, great. Well, we're out of time for questions. We'll move on to our third presentation, but I want to thank Karen and John and Joe for this presentation. Thanks. The final presentation of the afternoon will be lessons learned from integrating 1D and 2D Riverine and collection system models. The presenters are Jeremy McCall with Arcadis and Alicia Lanier with the City of Fayetteville, North Carolina. So with that, let's go to the video.
Good afternoon. I am Jeremy McCall. I'm a senior water engineer with Arcadis. I serve as the project manager for Arcadis on the Blunts Creek Watershed Modeling Project. Today, Alicia Lanier with the City of Fayetteville and I will be discussing the city's watershed modeling efforts and integrating one-dimension and two-dimension riverine and collection system models for the Blunts Creek watershed. I will turn it over to Alicia to discuss the city's watershed modeling efforts in today's agenda.
Thank you, Jeremy. I'm really pleased to be working on this program and participating in this talk today. My name is Alicia Lanier, and I'm a Stormwater Project Manager in the Public Services Department at the City of Fayetteville. To date, my role has primarily been to support the Watershed Master Plan Program and other special projects. So for this talk, I've been asked to give a brief overview of the Citywide Watershed Master Plan Program, how it originated, details about our wonderful team, and what we've been up to so far. And Jeremy will follow, and he'll carry the meat of the program. He'll describe the integration of the 1D and 2D Riverine collection system models for the Blunt's Creek watershed. And then I'll close with the next steps. The Watershed Master Plan Program was initiated after several large events, including Hurricane Matthew, Irma, Florence, and Dorian, on top of recurring frequent flooding from smaller events. And this is something we're all very familiar with. This combination of these large storms and frequent flooding prompted us to go to Council to ask for support to help us better understand and mitigate citywide flooding. And we were really fortunate that our Council had the vision to authorize a stormwater fee increase to help begin this program. Now, the primary goal is to identify potential projects that reduce flooding to feed the CIP and other programs. And as these projects are built, we know public safety will be improved and the city will be more resilient to future flooding events. So what does it take to do a citywide program and develop one from the ground up? It takes a village. Our team consists of city staff guided by our Public Services Director, Sheila Thomas-Umbat. And we're all supported by our program manager, Fries and Nichols. We have several consulting firms conducting the watershed modeling, and this includes Arcadis, Gradient, HDR, Wilpert, Kimley-Horn, and Hazen and Sawyer. And there are also two firms conducting detailed survey in the study areas, Stewart and ESP. Now, we understood or quickly found out that studying all 15 watersheds comprehensively would be a very slow process, extremely expensive and unnecessary in some areas. So in order to meet our objectives of using available resources, we had to develop an approach to prioritize the study areas. And as one foundational element, citywide modeling was used to inform the areas that should be studied in more detail. And you'll hear more about that approach in a separate presentation by Fries and Nichols. So now we're 2 years into the program, and we've developed some very, very good programmatic level foundational elements necessary. Now we have moved into detailed watershed modeling. So the first 5 watersheds under study include Blunt's Creek, Arcadis, Rockfish Creek, Gradient, Cape Fear 2, Gradient with HDR and Wilpert, Little Cross Creek, Kimley-Horn, and Beaver Creek 3, Hazen Sawyer. Stormwater assets have been surveyed in the study areas, stream assessments have been conducted, and H&H modeling has been completed. Now, Jeremy will cover some of this in much more detail. We've also begun ranking concern areas based on severity of the problem, and that's currently underway for several watersheds. And in phase 2, we will be evaluating potential projects to mitigate flooding in the highest ranked concern areas. And with that, I'll turn it over to Jeremy to discuss their role in the program and what they've discovered and what they're doing in integrating 1D and 2D models in the Blunt's Creek watershed.
Thank you, Alicia. The city's goal of developing a capital improvement plan for the Blunt's Creek watershed requires that the basin be modeled at a detailed level. As Alicia mentioned, Fries and Nichols performed a large-scale model using InfraWorks ICM. This large-scale study was used to identify 50 priority subbasins within the Blunt's Creek watershed. Arcadis was tasked with developing a detailed one-dimension hydrologic and hydraulic model in all areas and a two-dimensional model in priority basins using HEC-RAS for the primary riverine system and ICM for the secondary collection system. Arcadis was also tasked with performing a field assessment of high priority stream reaches and to identify erosion issues and problem areas that require mitigation with new drainage solutions. To develop a planning level model, we would have to take the following steps: delineate the priority subbasins, update the hydrological parameters, update the ICM hydrology and large-scale model created by Freese and Nichols. We would have to build the ICM hydraulic model network from the field survey of the priority basins. We would compare the calculated ICM flows to the existing FEMA HEC-RAS model and update the hydrology in the HEC-RAS model if needed. We would have to update the hydraulics in the HEC-RAS model based upon field survey and stream assessment. We would then run one-dimensional ICM simulations using HEC-RAS water surface boundary conditions. Those simulations would be used to identify where overland flooding would occur. These identified areas were then reviewed to determine where two-dimensional modeling was needed. We then would need to build the two-dimensional models for those identified areas. The model simulations were then used to determine planning level alternatives. A pilot study was completed to study options available to better model the flood spread and the surface routing between subcatchments without using two-dimensional methods. This was a way to determine if we could use an enhanced one-dimensional model to better understand surface flooding. The two-dimensional model shows how flow spreads across the surface. The pilot study looked at the means of seeing this, but also looking at how the flow may enter the system through other means, like crossing the street into another subcatchment and going into an inlet. Lessons learned from the pilot study are that the time of concentration should be selected based on the longest time, not the longest path. Stage storage should be identified with the invert of the storm inlet opening. Combine inlets on either side of the road into one inlet with double the stage discharge. The two-dimensional methods may be cost efficient and provide better results. And we needed to generate some GIS tools to assist with developing parameters. The project modeling has been divided into two systems: the primary system and the secondary system. The primary system includes the Riverine system. For the Blunt's Creek watershed, this includes Branson's Creek, Havers Creek, and Blunt's Creek. The secondary system refers to the stormwater collection system, including the storm sewer system and the ditches that collect stormwater and conveys that stormwater to the Riverine system. For the primary system, the existing FEMA HEC-RAS models will be reviewed and additional cross-sections and structures will be added based on available survey data. The only sections of the model to be updated will be those within the priority subbasins. For the secondary system, survey was completed within the priority subbasins. This data will be used to build an ICM representation of the stormwater collection system. The hydrology of the primary system will be a combination of the existing HMS modeling efforts completed as part of the system-wide hydrologic analysis, coupled with the flows generated by the detailed ICM representation of the storm sewer collection system. The boundary conditions for the ICM model will be taken from the HEC-RAS models within each priority subbasin. In this way, the two models will work together to provide the most accurate representation of how the systems work together in the real world. The first step of developing the planning level model is to update and build the model hydrology. We delineated the priority subbasins and then divided the priority subbasins into subcatchments. Priority subbasins were divided into subcatchments to provide a smaller scale, accurate model. We then created impervious and pervious layers within the subcatchments using GIS data. We then defined and developed hydrological parameters to calculate flows within the priority basins. The Blunt's Creek watershed consists of 7 square miles of drainage area and approximately 9 river miles. The Blunt's Creek watershed is the largest and most developed basin within the city of Fayetteville. Since this is such a large basin and the model needed to be compiled in a 6-month period, multiple staff was assigned to developing hydrological parameters and calculating the time of concentration. To accomplish this with consistency between staff, Arcadis developed 2 tools to assist with calculating time of concentration. The flow path tool and the time of concentration tool was created to expedite calculating the time of concentration. The flow path tool uses the DEM, building layer, and storm inlets to identify the longest possible flow path within a subcatchment. The output from the tools requires manual review before it is ready for time of concentration calculations. The time of concentration tool calculates the time of concentration based on TR55 and is adapted to meet the city's existing conditions. The time of concentration is the sum of three components: sheet flow for the first 50 feet in urban areas and 100 feet in rural areas, overland flow, which is based on surface conditions, channel flow that depends on upstream contributing area for the stream, and standard channel sizes that are provided by the city. The output from the flow path tool requires manual review. The team also developed flow paths using Arcadis. These flow paths were compared to help identify paths that needed to be corrected. The flow paths were then manually reviewed. There are 5 typical areas that would need to be corrected: where the flow paths did not reach the storm inlet due to DEM and slope issues, where paths were determined to stop at buildings instead of wrapping around the building, where DEM issues created extra points vertices on the flow path, where the flow path was flowing in the wrong direction, and where incorrect delineation boundaries were shown. The flow path tool uses the digital elevation model and raster images to create the flow paths. Issues with the raster images and flat slopes caused the flow paths to not connect to the downstream inlet. Flow paths were manually extended to the downstream inlet. Flow paths were reviewed to ensure the paths are the real longest path available. As you can see in the middle picture, paths are cut off by the building layer, so the tool considers them a shorter path. Merging paths and making the paths wrap around buildings creates the real longest path available. Cleaning up of the flow paths are required for accurate time of concentration calculations. Flow paths were reviewed to remove extra vertices that were created by raster processing. Some outputs show the flow paths flowing in the wrong direction. This occurs due to flat slopes and raster image processing. The direction of flow of these paths were corrected as needed. The flow paths generated by a flow path tool will show where subcatchments were delineated incorrectly. These delineations were corrected. On the last couple of slides, I focused on the manual review of the output from the flow path tool. Even with these manual reviews, it saves staff hours of time and provided consistency across staff tasked with creating the flow paths. Once the flow paths are corrected, the time of concentration tool is used to calculate time of concentration. This data, along with the DEM, rating curve, storm inlets, land use parcels, and rainfall depths were inserted into the ICM model. The ICM model would then calculate the flow, the total flow path, and rating curve with an updated time of concentration. The next step to creating a detailed model was to build the hydraulic model in ICM. The field survey information provided by the city was used to build the hydraulic model in ICM. The storm system, inlets, and culverts were imported into the model. Open channels were then created in the model. Manholes and stormwater structures were imported. Nodes and locations of inlets and pipe size changes were added to the model. Stage area relationships were developed for the subbasins and were assigned to the subbasin loading node. A stream assessment was performed for the Blunt's Creek watershed to verify locations of bank erosions or threatened infrastructure within the high priority subbasins of the watershed. A desktop review was initially completed to locate reaches of the creek that are on the North Carolina Department of Environmental Quality's list of 303D impaired waters. Historical aerial images and land use information was used to look for signs of erosion, research soil erodibility factors, and to locate areas of potential threatened infrastructure and identify crossings of utilities or roads. The soils shown within the high priority subbasins are all below a soil erodibility factor of 0.4, which is defined by the USDA as moderately erosive soils. The areas identified from the desktop review were reviewed and approved by the program manager. A bank erosion hazard index stream assessment was performed in the field at the identified areas. Assessment data was collected in the ArcGIS Collector app with components of the Beehive filled in during field evaluation and the Beehive value calculated upon return to the office. The data gathered from the stream assessment will be used to update the HEC-RAS model and assist in identifying areas of concern. The modeling of the storm sewer network will be completed initially using enhanced one-dimensional modeling methods. These methods include using storage nodes to simulate spread of overland flow within each subcatchment. Typically, modeling teams use one-dimensional modeling techniques to isolate where flooding occurs and two-dimensional modeling to determine how the surface flooding spreads over the area of interest. Our modeling team is looking into modeling the subcatchments with the means of showing the spread during the initial one-dimensional modeling efforts. The premise being that we can prioritize the two-dimensional modeling efforts based on a better understanding of the impacts of the surface flooding to the area of interest. In addition, we are adding gullies between the subcatchments to provide the means for flow to move between subcatchments rather than just to flood the surface. This will better represent how flow actually moves along the surface. The one-dimensional modeling efforts will provide the basis for the two-dimensional modeling efforts. The surface flooding noted during the one-dimensional modeling will be evaluated and prioritized based on volume and spread. Surface flooding will be noted for a variety of storm events from the 2-year to the 500-year 24-hour rain event. The primary and secondary systems will be evaluated under existing and future conditions. The level of service expectations have been set for surface flooding. The level of service requirements will be used by the modeling team to prioritize two-dimensional modeling efforts, with specific attention will be paid to potential impacts to buildings, essential and non-essential. Per the current scope, two-dimensional modeling will be completed for both the primary and secondary systems. The two-dimensional modeling will provide a more robust understanding of the surface flooding spread and potential impacts of roadways and buildings. The modeling team will use the results to identify areas to focus mitigation strategies. These areas of concerns will be rated and reviewed in detail with the client.
Thanks for all that information, Jeremy. So as you can see in the flow chart, once the concern areas are identified, we put them through this decision-making process to determine whether or not potential projects should be evaluated to mitigate the concern, and includes several steps, but it's based primarily on the severity of the problem as defined by lengths of lanes closed from flooding, hazardous crossings using depth times velocity, how many structures and what type of structures are impacted, which, if there are any essential facilities impacted, and access concerns. And then we also look at stream concerns and in a separate flow chart. The city then, we will review the concern areas with the consultant after they've been ranked and the core management team. And we help determine whether or not to move forward with evaluating potential projects. So once that decision is made, Jeremy and his team, for example, will move into refining and modeling selected potential projects. And including, we'll be looking at future conditions, considering economic development overlays, and developing opinions of probable cost. And after that, projects will be prioritized for inclusion in the CIP and other programs. So that's phase 2. That's where we're at. And with that, we thank you for your time, and we'll take any questions you may have.
Welcome back to the question and answers. For those of you out there, this is the third presentation. Anybody who has a good question, please submit it. We're not having a whole lot. I realize this is the end of the day, but we'd love to be able to ask a few questions here and get some more information. So with that, the question on the board, what is the ICM model? I haven't heard of it before.
Yeah, I'm going to apologize for not describing that well. It's the InfoWorks ICM model by Innovaz. That is the software that was selected by the city to for all consultants to use for consistency across the modeling work.
Okay. Question here regarding a term that was utilized in the presentation, severity of concern. How is this actually, or has it been quantified for prioritization?
I think the severity of concern is relating to the selection of the priority basins. Friesen Nichols completed those, analyzed those basins. They actually did quantify those with a matrix, evaluating impacts to structures, high water marks, and other impacts.
Yeah, and I'll just jump in for a second too, Jeremy. And in the context of if that was something that I had mentioned about concern areas leading to project prioritization, then we're also taking that a step further, what Jeremy just said, and evaluating the severity of the problems that we're seeing in these high priority subbasins, and using that kind of ranking and scoring to help drive our decisions of which concern areas we'd move forward with to evaluate, our consultants would evaluate projects for. So kind of a two-step process.
Okay, the next one's really not a question, it's more of a comment, but I'd be interested to hear your perspective on it, Jeremy. It says, using rain on mesh modeling in ICM can provide a better flood representation than using predefined drainage areas. Any perspective on that?
I think I can agree with that to a point. I think in this project, we provided a standards document that guided how we modeled the basins for consistency amongst all the consultants. So that's what we went with.
Okay. Question here is, what schedule do you anticipate to complete phase 2?
Alicia?
Mm-hmm. It's a staggered schedule. So you're talking about Blount's Creek. I think you guys have, let me think about it for a second, Jeremy. I've been so focused on the projects that we're trying to get out in by October for a couple of other watersheds. And I think y'all are early spring, early summer next year. Does that sound about right?
Yes.
Yeah.
Yes.
Okay, next comment was, great work. Does the flowpath tool include stormwater structures in the DEM?
I think that the stormwater structures were imported into ICM from the survey. And I think the DEM was also imported. So it could be a combined question, answer of yes.
Okay. Do you have problematic flooding issues that were validated by the model? If so, did the model help direct you towards mitigation?
At this point, we use the water condition boundaries from the FEMA HEC-RAS models to validate our ICM models. And we're in the process of completing those models and looking at recommended projects. So I don't know if it's directed to storage mitigation yet on that direction.
Okay, we've got that one. And then I've got another question. Did you tie subsurface flows with overland flow using ICM?
Yes. ICM is a fully integrated 1D and 2D software, so it does take into account the subsurface flows with the overland flows.
Okay, well, as it stands right now, that's all the questions I've got in here. They've all been answered. If something comes in, I'll quickly ask it, but if not, we'll take time to thank all of our presenters. The first presenters, Siva and John Payne, and then our second presenters, Karen, John Hood, and Joe. And then our final presenters, Jeremy and Alicia. But In absence of any further questions, I want to thank everybody for tuning in on this, providing the questions. And with that, I encourage everyone to visit the exhibit hall now. I think there's some after-hour social activities there. I think there's a trivia contest tonight or in the near future. But check that out and hope to have you back tomorrow and the day after to continue with this effort. But with that, I say everybody have a nice evening and look forward to hopefully running into you tomorrow. Thanks.